We'll start with these sound check questions.
Yeah, sure.
What was your first computer?
It was an Apple II, I think.
Okay.
Yeah. It was that. I guess that was my second computer. My first computer was a teletype connected to a mainframe.
Favorite keyboard shortcut?
Favorite keyboard shortcut? I guess I would say is WASD.
Yes, yeah, a gamer at heart. Cool. If you do some programming, would you use tabs or spaces?
I would tab. I like tabs.
And then, what's your favorite programming language?
Well, the one that I spent the most time with was Fortran,
Uh-huh.
and then I guess Pascal. But the one I guess favorite would be awk.
Ah, you're not the first person to say that.
If I think about what I program on a day-to-day basis, I probably most often use awk, and I often use Python for things where awk isn't big enough, or, doesn't scale up to bigger things. And after that, it's kind of a toss-up.
Awk has been said before, then I'm glad to hear it again.
Yeah.
What's your least favorite programming language?
C++.
Okay, cool.
That's why the people who do it so well are so incredible.
Yes.
Yeah.
What was your first computer game?
My goodness. I guess it would be Asteroid.
Very good, like that. And then a sneak peek at the next one. Do you prefer tea or coffee?
I used to prefer coffee, but increasingly I'm preferring tea.
A little birdie told me that one of your hobbies is reading archived papers. What sorts of things do you look for?
Well, a lot of them are too deep, but if I scan over it, I always learn something. The latest one I looked at was of course, the DeepSeek R1 paper, and how they used reinforcement learning without supervised fine-tuning, and got really good results.
DeepSeek, we did a video about it. It was rather popular, as you might have imagined.
I bet, yeah. These days, you don't even have to read the papers anymore. I just load it up into ChatGPT, and I ask ChatGPT to read the paper for me.
That was what I was going to say.
Yeah.
If you're going through past papers, and sometimes you can just use the AI as a tool to help you with the sort of summarizing, I suppose.
Yeah, summarizing it, but now you're asking it questions. So in a way, you're talking to the researcher, which I think is completely brilliant.
We're past the Turing test, right?
That's right. The thing that people haven't internalized is when they use AI for summarization and research, when you're done, you actually have an expert researcher
Yes.
of that topic. And so, recently I was doing some stuff on silicon photonics, and when you're done, you have somebody you could talk to about silicon photonics, the old days and the future and who's doing what. And so on the one hand, you could ask it a whole bunch of questions that you didn't even know was in the research, questions you didn't put into research. And so, yeah, it's really fantastic. When you're done, you have an AI.
Obviously, it's running on the GPUs and a lot of Nvidia technology. But I'm intrigued, if we just go back a few years, we had different kinds of GPUs for different tasks. So, when I started video editing, you used to use a Quadro card, or if you were gaming, you would use a GeForce card. And so those architectures, why would you use different cards for that? And how's that changed?
Yeah. The one thing they all have in common is CUDA. However, computer architecture and the different applications of computing could have different mixes of the different resources that are in the GPU. Maybe we decide that one GPU has more texture unit, and maybe another one has more ROP. Maybe another one has HBM memory. Maybe another one uses graphics memory. And so those are kind of product feature type things. At the computation architecture level, some of the GPUs have better double precision floating point. Maybe some of them are really good for graphics. For example, it focused largely on FP32. But increasingly, they all use tensor cores. And the reason for that is because whether it's computer graphics or whether it's AI, or even now physics, we use AI in all of those fields. And so tensor cores are now a larger and larger component of graphics. Tensor cores, of course, is the central component of our AI GPUs. in computer graphics, we render 1 pixel and we infer the other 15. I mean, it's kind of incredible. We're only computing 1 now, and we're guessing about the others. And yet they're temporally stable, and the color predicted are exactly what we thought we would see. And as a result, we can render much higher resolution, much greater complexity, and the image is actually better than you could have done using completely rendered approaches. And so AI isn't an approximation. AI has expanded really the reach of physics and almost every field.
Are they still split into different types, or is that what you're saying? They're kind of converging so that you're using the same kind of tech in all sorts of different things, creation, as you say, physics modeling, all these different things. They're using the same kind of stuff now.
The first major fork was when we took computing with double precision and computer graphics with very low double precision. We try to make sure that every program will run across every GPU, even if slow. Compatibility is the first job of a good architecture. And so we, in the case of computer graphics, maybe we'll have 32-bit floating point, but the FP64 is rather slow. In the case of scientific computing, FP64 is at its limit and should be as fast as possible. That was our first fork. But then the second fork came when we realized that tensor cores for AI in a data center was becoming, and AI processing was so much more important, that we added more and more and more tensor processing, and increasingly we're slowing down the advance of FP64. And the reason isn't because FP64 isn't important, but ultimately you need the space for something, and you need space to do anything. And so we believe that the right approach now is to lean more into tensor cores, do more emulation of double precision, and as soon as possible move towards not just purely principal solvers, but partial principal, partial emulation, partial AI approaches. And these hybrid approaches are much, much more promising, and so we're going to lean into that. In the case of computer graphics, then it went off into FP32 and programmable shaders, but at some point we realized that AI could really make a difference. So we took the tensor core that was in our data center and we moved it back into computer graphics. And so the story arc kind of said, GeForce brought CUDA to the world, and CUDA enabled AI. The CUDA GPU gave every single AI researcher a supercomputer on the PC. And so CUDA enabled AI, but then it's amazing that AI came back to revolutionize GeForce. So it came back to the house it built, and now computer graphics is really AI driven.
I think it's fair to say that the pace of change over the last few months has been quite relentless in terms of things like AI models and what have you, DeepSeek, Manus, all these different things. How do you plan for that? I mean, it's relentless, right? And also on the hardware side, you're obviously moving very fast to try and kind of get ahead of that. And when I heard that the models are getting twice as fast every 7 months, which is incredible, isn't it, right?
The models are getting twice as fast. The amount of data is also accelerating quite fast. The product of it is the amount of computation we need. And so every single year, we could be increasing the amount of computation requirement by a factor of 10. And now, so the question is how. There's probably a question about why, and then there's the question of how to keep up. And at the core, starting with how computing is scaling, there was a time when software was prepackaged. That's kind of the beginning of it all. We prepackaged the software, we put it onto a CD-ROM, we sold it over retail, and so prepackaged, precompiled software forced the scaling of computers to be limited by this concept called Moore's law. And it was limited only by semiconductor physics and CPU architecture, and of course we went from microcoded to pipelining, we went to superscalar, we had out-of-order execution and all the crazy technologies we now use for branching, and And so we're looking for instruction level parallelism, and we're doing as much parallelism as we can, and we went to vectors. And the CPU architecture advanced as quickly as it could, but in the final analysis, it could only make the software run as fast as it was packaged to do. And so the software was prepackaged. The thing that was a real breakthrough is when we went to accelerated computing, the software package could still remain the same, but using CUDA, we could introduce new algorithms and replace the algorithms underneath, and therefore the GPU underneath at the same time. And so the benefit that brings is you now have a co-design benefit. It's called co-design. Basically, you have a full stack optimization opportunity. Instead of being constrained by the box that you're in, you now left the box. You could architect the software, the algorithm, and the chip at the same time. And so you could optimize much more openly. It allowed us to accelerate software much faster than Moore's law predicted. Now we're doing something even more than that. And so with AI, we could, of course, change the precision. It's a statistical approach anyways. If you wanted to add two numbers, 1.1 plus 1.3, and if the answer was going to be 2 anyways, or 2 point something anyways, does it really matter how much precision you have? And so approximation is a fine approach for AI. And so now we could improve not only the architecture, but also the quantization. And every time we went from FP32 to FP16 to FP8, we're effectively quadrupling the amount of computation or reducing the amount of energy by a factor of 4. We could also change the structure of the computation. Instead of vector algorithms, vector approaches, the computation structure is much more efficient. And so we could very efficiently fetch and execute 32, 64, 128 instructions at the same time. And so the computation structure of the chip could change, and we call that a tensor core. And now the structure of the computation matches the nature of the algorithm. And so anyways, we're changing so many dimensions of computation at the same time. And now when you go into our data centers, we once you parallelize an algorithm, you could parallelize it on our chip. But why can't you use multiple chips? If you can multiple chips, why can't you use multiple nodes, multiple racks? And so now the parallelization approach has gone to data center scale. We went from being limited on one chip because of prepackaged software to now being able to optimize across the full stack, to optimizing the algorithm and the precision and how you parallelize. The dimensionality of scaling has gone out of control. I mean, it's incredible. And so in the last 10 years or so, we probably increased computation scale by probably a million X or so. Moore's law would have said 10 times every 5 years, right? 100 times every 10 years. So instead of 100 times, we went a million times. But what's amazing is, while we're sitting here making computation of these neural network models faster and faster, new architectures of neural networks are being invented. And the reason why that's possible is because people think the neural networks as these rigid structures, like neurons connected somehow. But it's not like that. It's software. It's expressed as a neural network.
It's malleable, right?
Yeah, exactly. It's basically software. And so it's completely free of being reinvented. What was transformers is really, in a lot of ways, a concept. And now transformer has really evolved into these incredible structures. The innovations that go along with that, and all of the interesting approaches of making microprocessors go faster are now helping transformers go faster, and speculation techniques, and multi-token prediction techniques, and all kinds of different compression techniques are now being applied, and so even the transformer algorithm is changing.
You also mentioned Moore's law a couple of times there, and as I understand it, Moore's law originally was about how many transistors you could get on the silicon, right? Your kind of roadmap is showing that the density of the GPUs or the cores is crazy.
Before you scale out, you have to scale up.
I heard you talking about scaling up, scaling out. Can you give us a sense of what the difference is, what that means?
Yeah. Scaling up is to take the capability of a computer and with very limited change to the software, make it go way faster. Scaling out is really about taking the algorithm and then breaking it up into a lot smaller parts that could be, largely distributed and spread the work around. And so scaling out would be something like Hadoop.
Google originally came up with the whole MapReduce idea, and then it got popularized through an open source implementation called Apache Hadoop.
And Hadoop would be a scale-out computing approach. And scale-up is when you make a faster and faster microprocessor. But scale-up is extremely hard to do. You're limited by the limits of the semiconductor physics. You're limited by memory bandwidth. You're limited by just about everything. And so we invented this thing called NVLink, which made it essentially possible for us to connect a whole bunch of GPUs together. And they're talking to you program those GPUs as if it's one giant GPU. It's not exactly true, but it's close to true. And so scale up gave us the opportunity to create essentially a giant GPU that semiconductor physics can't possibly enable. And then once we scale up as far as we can, then we try to scale out by connecting multiple racks together, multiple computer racks together. And that's the most efficient way of doing parallel processing. It's a little bit like, it's great to have teamwork, but you really would like to have the smartest possible people, the most productive people, and the smallest team. It's
without having meetings.
Yeah, people have these. There's a limited ability for teams to scale, and the reason for that is because the overhead of communications and coordination, and all of their coordination with each other.
The mythical man hour.
The mythical man hour. That's right.
Absolutely.
Exactly. And so scale up stays within that mythical man hour because on our GPU it's already parallel. That's the big invention of CUDA. To how to program in a way that on the one hand is parallelized, on the other hand looks like one application. The modern way of scaling out computers really stem from the programming model of CUDA, and we're just taking it to the extremes.
But because you mentioned that like the modern way, as in having CPUs and multiple cores, obviously that's parallelized. Do we still need CPUs?
Sure. And the reason for that is, Amdahl's law. At some point, something is sequential. And if there's something sequential, you want to use the right tool for that. Let's say sequential processing was only 10% of the total compute time. And that 10% had to be done step by step because the dependency is such forces you to do that. However, the other 90% could be parallelizable. If you take that 90% and you sped it up infinitely fast, you still have that last 10% left. And so even though you have an infinitely fast computer, you still have 10% left. Moore's law, or Amdahl's law, limits you to that. Now, if you took that 90% and you sped it up, to only a unit of that 10%, now you've only sped up the computer 5x, even though it seems like you've sped it up 10x. And so that last sequential part, you want to make as fast as possible, actually. In a parallel computer, you want to make the single-threaded computer as fast as humanly possible. And so that's why we build our own CPUs, so that we have excellent single-threaded performance. Everything else that's multi-threaded, we could offload on CUDA to do. So what remains is single-threaded, and so we.
There's probably literally one question I'd like to ask, which has actually come from my colleague Brady.
Yeah.
Brady runs a channel called Numberphile, which is a mathematics channel. And he's aware that the largest prime number was calculated on Nvidia equipment by one of your former employees, Luke.
Yeah.
He wants to know, is there any unconventional use for the technology, that you perhaps didn't foresee that tickles you?
There are all kinds of interesting applications that we wouldn't have expected. And they're all real-time applications. CUDA is incredible at high throughput. And high throughput computation tend not to have real-time response. But over time, we've improved the coordination between the control loop and the algorithm loops, that many applications that are real time in nature, but also heavily computational, can be used. And one of my favorites is actually the 5G radio.
Okay.
You know, instead of having full custom chips that are doing the radio baseband processing, we do the baseband processing on CUDA. And the amazing thing that's really great about 5G radio on CUDA is now that the 5G radio is software defined, then you can layer on top of it or interact or intermix AI into it as much as you like. And so we might be able to replace layers of the pipeline with AI. For example, we might be able to do a fully deep learning based radio network, baseband signal processing layer, or we might be able to use AI at the massive MIMO layer, or we might be able to use AI to orchestrate the traffic across multiple radios. And so now AI RAN is possible. And the idea that a radio network would essentially be a robotics network makes a lot of sense. Then the next thing you would apply to that is reinforcement learning, and now the algorithms can be quite adaptive and quite autonomous, and the amount of energy we might be able to save on the radio network could be quite substantial, and we might be able to expand the spectrum efficiency quite significantly. Now, some of the things that are exciting about communications, of course, is that when you apply AI to the communications network, you might be able to increase the effective bandwidth surprisingly high. And the reason for that is because you don't have to keep transmitting the same signals, because you already know what that person looks like. Like, for example, in video conferencing, once after first couple 2-3 frames, maybe the rest of it don't have to be even encoded. We'll just predict it based on the sound that you hear. And so from the sound of the voice, you could reanimate the face very easily using a neural network. The amount of bandwidth we use on 5G or 6G could reduce, 1,000x, all because we have AI now. And if you add on top of the transmission human priors, human prior knowledge, all of a sudden the generative process on the other end, we could replace network bandwidth with neural network computation. And so, all kinds of interesting things like that might be possible.